But I do want to talk about the evolution of the landscapes in these river systems in southeast Texas, and with the intent of helping to understand why these different rivers behave differently, and particularly with respect to flooding and flood-related issues. Now, we've got a lot of rivers here, but I'm going to look at four, and the largest of which is the Brazos River. The Brazos River is a drainage area of over 45,000 square miles. Another river that is of local interest, but I will be ignoring, is the Trinity. And then we see the San Jacinto River, which is 1/10 the size of the Trinity. And then if we add Barker, Brays, Buffalo, we see these are really little tiny rivers. And so it's not a surprise that their geologic origin is different, that their morphology is different, and they have very significantly different problems with respect to flooding. Okay? Now, let's just look at the Brazos, and let's see. Okay, and the San Jacinto. So we're going to focus on the largest river first. And when we look at large rivers in any coastal setting, we have to recognize that their history is, to a large extent, predestined by climatic change. We heard the last speaker talk about how climatic change, or as the government insists on saying, non-stationary climate, but as climatic change is going to affect the future, the past climatic changes have significantly affected these coastal river systems. And they've affected them because of changes in sea level. We've alternated for the last million years or more by intervals of glacial and interglacial periods. And during those glacial times, it's been cold, sea level has dropped, and during the warm times, it's been interglacial, it's been warm, and sea level has been higher. And if you look today, we are here at this high stand of sea level, present sea level. If we go back 120 million years or so, 120,000 years rather, it was high again. But in between, we had a major drop in sea level. Okay? And in fact, if we look at the history of the last 100,000 years, sea level dropped to almost 120 meters below the present. And then very rapidly, over about 20,000 years, it rose. And sea level is the determinant for how rivers are responding with respect to entrenchment and deposition. So what we saw 18,000 years ago was not only glaciers over much of the northern areas, but also the Brazos River, as an example, flowed to a shoreline that was 100 miles offshore. And it also dropped in its size. And so what it did, it became a valley. And there was a valley, this is the Mississippi, but in the Brazos, and the Trinity, and the San Jacinto, these valleys were 40 meters deep in some cases. Okay? And so as sea level began to rise, those valleys began to fill. And the nature of the fill changed as climate changed. And eventually we got to near a point where sea level really stabilized. And so this is the present high stand sea level. So the modern rivers today basically have been around for about 4,000 years within these large rivers, of which the Brazos is one. And so you'll notice that this particular river system, the floodplain, hasn't quite filled the valley. So we can see that today with the modern Brazos. We have the modern Brazos, which is actually sitting within this Pleistocene valley. And in fact, there we see that there's about 40 meters of fill beneath the Brazos Valley. And it's surrounded by these Pleistocene uplifts. Now the river itself, you see, is rather complex. This is the river today, but there's clear, abundant evidence that this river has changed its course through time. And that area between the valley margins is what we call the geomorphic floodplain. And I want to distinguish that from the hydrologic floodplain, because in some cases they're significantly different. And within the geomorphic floodplain, we see the history of the river changing its course over the last 4,000 years. We can look at LIDAR data or DEM data. It just tells the same story, that there's this very broad floodplain within the large rivers like the Brazos, within which we have these meandering rivers. Now this is a cartoon version of a geomorphic floodplain, and notice that when it flooded, the area that was flooded was not the entire valley floor. So that the hydrologic floodplain can be smaller, and it can also vary. Clearly, the flooding of a 1% flood is going to be less extensive than a 0.2% flood. So let's just look at the 100-year floodplain for convenience, and we subdivide that into a floodway, which is a somewhat complicated definition, but it's a constrained portion of the 100-year floodplain. Let's, for sake of argument's sake, pretend like it's a 10-year floodplain. And it has special regulatory requirements within that. And then the rest of that floodplain is the floodway fringe. And that's the area where people can build as long as they don't impact flooding the floodway too much. Now here's our geomorphic floodplain of the Brazos. And here we see the floodway and the floodway fringe. And if you look carefully, you can see that a very significant portion of the floodway fringe is actually protected by levees and covered with subdivisions. So we have, in the case of around the Missouri City, we have most of the floodplain and almost all of the floodway fringe outside of the flooded area protected by levees. Or at least that is, of course, the intent, or the intention of those. Okay? Now, if we look at how wide that area is, we're looking at something like 8 miles of floodplain, or potential floodplain. And the floodway itself, huge, 2.5 meters. Compare that to the San Jacinto River. The San Jacinto River, which is also an incised valley that's been filled with the rising sea level, has a floodway of 1.5 miles, a total flood, 100-year floodplain of 2.5 miles. Okay? Notice the difference in proportion, though, of the floodway fringe to the floodway. And this reflects the size of that valley. Because what happens is the hydrologic floodplain of the San Jacinto River is sufficiently small, the geomorphic floodplain, sufficiently narrow that it floods completely. Whereas the Brazos River, which has a much larger geomorphic floodplain, has a much more widespread flooding area. But all this talk about flooding has bored me. Because I'm interested in addition to flooding, what happens during a flood? And that is that rivers move. They make lousy geographic boundaries, or political boundaries, actually. And they move by really 2 processes: lateral migration and avulsion. And avulsion is a rapid change in the location of the river. And it could be a relatively local one, like a meander cutoff, or it could be a valley scale avulsion, where literally the river completely changes its location, such as occurred 1,000 years ago with Oyster Creek. Now here we've got that old, abandoned, meandering river. Here we have modern rivers. Meandering rivers are the norm, particularly in the coastal plain. So here's an example of a meandering river, and what we see is on the outer bank there's erosion, on the inner bank there's deposition. And if you look closely at these lines of trees, you'll notice they form kind of arcs. And those arcs are what we call meander scrolls. And they represent the location of that river's edge at different times. That's new land that's been added. What you can't see is the land that's missing. But an equivalent area of land has been removed as has been deposited. And so these meander scrolls, or these ridges, are our geomorphic record of lateral migration through time. Now the other thing that's happening, we have not only the deposition of that sediment due to lateral migration, But we also have vertical accretion, because when the floodwaters go over their channels, they drop their load. The coarsest and greatest amount of sediment is immediately adjacent to the channel, forming levees, and then it grades out into topographically lower and finer grained clay-rich flood basin deposits. And this is an important point, in part because it causes the river, the meandering river, to become a ridge. It's actually topographically higher than the rest of the floodplain. And as these rivers move, it changes the morphology. And remember, inches matter. It changes the elevation of the floodplain, and therefore is a major determinant in what areas flood and what areas do not. Now, as geologists, we've been looking at meandering streams for a long time. We see that they move laterally and deposit sediment. And in fact, this is too much like a geologist would show. Let's look at this. Look at how this river has been moving laterally. And basically, it's been accompanied by erosion and deposition. Okay? Now, a petroleum geologist would see that deposition. This is our potential reservoir. The levee, the channel bar, and we're going to focus on that. Well, not here. But the engineering or environmental geologist looks at it land lost, the land you don't see. It looks at land lost, it looks at vertical scouring, and deposition itself can be a hazard, can be a problem. So we're going to be looking at how these meandering rivers change and how, in addition to flooding, how erosion and deposition are problems. This is a typical scene of the Brazos River. If we look at it from the air, we can see that we see the cut bank. The cut bank in action might look something like this. And as Dr. Matheson said, you always need a cartoon. So they say, I can't believe you got such a good deal. What's in the other room? I'm afraid of the look. And it's maybe less cartoonish than you think. Because FEMA, which is concerned with a lot of emergencies, has been concerned with flooding for a long time, but they also recognize that river erosion is part of the problem that we need to deal with. And so as early as 1994, FEMA was required to evaluate the technology for erosion hazard areas. That's, by the way, that's on the coast, coastal erosion, as well as rivers, and how it might impact the flood insurance program. Because it turns out they were paying out a lot of money, flood insurance money, for non-flooding, or better said, flood-induced erosion. And about a third of the nation's streams have been having serious erosion problems, so to the tune of something like $500 million a year. So here we're thinking, do I need flood insurance? Well, actually, yes. You do. We all do. And ironically, erosion is even in some ways more problematic than flood inundation because it can destroy houses well outside the regulatory floodplain, although we've seen so does flooding. But it destroys the structure and the property. You can't rebuild if there's no land there. And so unlike flooding, you can't simply raise the house and build again. And it can be under relatively lower flood conditions. It can be progressive and gradual. So it can result in cumulative long-term losses. So these erosion hazard areas that, frankly, we don't pay much attention to are areas where, on the basis of lateral erosion or avulsion, you might lose a building or land within a 60-year period. Now, I probably won't have time to talk about that much, but there's a whole area of discussion that people related to concern with flood risk need to be thinking about. Okay. Now here's a LiDAR image of the Brazos, and we see these meander scrolls sitting down there. They show that lateral migration of the river. They show this area of topographically higher land from overbank flooding, levees, and related features. Okay. And they show over here, this meander loop is getting larger and larger. Okay. Well, eventually, those meander loops can get so large that they can be cut off. And this is a type of avulsion called neck cutoff. And we see a variety of examples of that. Take a look right here. That's what we call a neck cutoff. Okay. So if we look at the Brazos River, we could actually look within a 100-year period of time, and we see it's been moving all over the place. Okay. And so what we can define, among other things, is a historical channel change zone to give us a sense of the mobility of that river. Now, in fact, what we'd like to use is use this information to anticipate future erosion. And so if we look at around Richmond and Sugar Land area, we can see where the river has changed, and there's been critical areas of erosion defined. Now, a critical area is erosion where something is important is being eroded, because erosion is occurring all over the place. But when we look at those critical areas, we see they are at the cutbacks. So we have remarkably noticed that erosion occurs on the cutback. And so, at what rate is it occurring? Well, here we can go to Google Earth and take a look down here, and we can see that this area is eroding at a rate of about 13 feet per year. That's pretty impressive. And we can look at some of the others, 12 feet, 8 feet. So this is one of the ways we can extrapolate and to try to define an area of future risk and or decide to try to anchor the river. Okay. Now, eventually, rivers can cut off. In fact, a nice example of that is in the lower Brazos River, where 1964, here was the neck of the meander. In 95, doesn't look too good, and after Alicia, we're looking at meander cutoff. And of course, Oxbow Lake is we're apt to say. So these Oxbow Lakes are evidence of early prior avulsion. Okay? Here we see another example. In fact, any freshman textbook will tell you this story. Okay? The problem is, let's take Simonton on the Brazos River. They've got a serious problem. And I saw this in the newspaper and I said, why is that man pointing out a meandering loop? It seemed kind of odd. Maybe he was a geologist. But he was the mayor. And they had both flooding and erosion problems. And so the question was, how bad is the flooding? And if it's bad enough, should we do dikes or other levees? But by the way, if they're levees, are they going to be around 50 years? Because the Corps has this annoying habit of wanting to have things last for long periods of time. So, first answer is those were 10 to 15 year floods. So, they've got a flooding problem. But if you look at Simonton in 1958 and then in 1955, you can begin to see the problem. Because as we look at the river edges with time, we can define that erosion. And of course, what's happening is there will be a meander cutoff. And unless you can somehow stop that erosion, which is possible, but expensive, and it has downriver impacts as well, you're going to be looking at the Brazos Lake as opposed to the Brazos River in this area. Now, as these rivers kind of meander back and forth, they don't meander too wide, and so they form a belt, what we call a meander belt. And it's a little elevated because of those levees, and it drops down into a broad, low floodplain. Well, at some point, particularly if the floodplain is wide enough, you have the potential for that river changing its course. And what it does is it finds a shorter, lower route. And so it goes down what used to be that floodplain. And now it's got a new meander belt. So this is the process of avulsion. Okay? And this is just an example of one river that did it. It used to come down here, and now came down here. But we've got a better example. We've got Oyster Creek. Oyster Creek used to be the Brazos River. In fact, this is the Paleo-Brazos from 4,000 to 1,000 years ago. And I've defined that meander belt, if you like. Okay? And 1,000 years ago, it shifted. And this caused a major change in the drainage pattern. Well, in fact, there was a meander belt before Oyster Creek, and then Oyster Creek, and then the one we haven't dated, and now the modern one. So you see that the valley, in these wide valleys, with these big rivers, can have a whole series of these meander belts. And these are topographic features. And the areas between them are the lowest areas and most likely to flood. And so sometimes these older meander belts tend to be the better places to be. And we'll see that's the case. I mentioned that there are levees. Much of the floodplain now is covered with levees. They're owned and maintained by individual districts, and they protect something like a third of the county's taxable assets. So Fort Bend County really wants these areas to be safe. Okay? And the problem is that they do protect houses and create income. But one of the difficulties with levees is that you block off what was the floodplain and you use it for something else. We have to recognize that floodplains have value in and of themselves, and I would suggest Acadia Prairie being an example of an area which has intrinsic value that maybe is not best served by completely covering it with subdivisions. But the other problem, maybe more problematic, is that levees can fail. We saw that in Katrina. We've seen it on the Mississippi. We saw it almost happen in the Harris County area. Maybe they're overtopped or poor maintenance or erosion or subsidence or undersapping. But when they fail, then they become dams and they accelerate the flooding. And of course what happened in the 900 homes that were flooded in these leveed areas along the Brazos was that the failure was not of the collapse of the levee, but rather the drain systems didn't work. And it rained so much that we're in a subdivision with rain coming down behind us, and we got a dam that's backing up the water. The dam is the levee to protect us from flooding from the river. Okay? So we've got issues here that we need to recognize. The other thing is because these big rivers, and we talked about this earlier, have a much larger area to drain. Not only is their time of concentration or lag time longer, but also they flood longer. So the Braze Bayou flooded for a couple of days. The Brazos River flooded for 7 days. So we have more long-lived flooding as well as more widespread. Now the last thing I'll mention about the Brazos is once it reaches the coast, it begins to bifurcate and split. It begins to switch its course because it's no longer confined by the valley. It's actually filled its valley at this point. It's beginning to spread laterally. Okay? So we're going to come back to that to see how this happened in the past. Now, if I were to summarize then, the Brazos River floodplain has a very large discharge of water and sediment in a large drainage area, so it's got a very wide valley. Okay? It's got a high sediment load. What that means, by the way, is that it was able to fill the bay that was formed when sea level was rising. That's unlike the San Jacinto and Trinity, which don't have enough sediment, so they empty into Galveston Bay. The geomorphic floodplain is wider than the hydrologic floodplain, and it has abundant avulsion events, both meander cutoffs and valley scale changes. Erosion is a major problem. Much of the floodway is occupied by levees, and that causes unique issues. Dams aren't a major factor in the lower Brazos River. There are relatively few sand mining operations, although some of them are clearly in violation, and floods are usually of longer duration. Now let's compare that with the San Jacinto River. The San Jacinto River watersheds are broken up into several smaller sheds, and I'm going to focus on, I'm going to ignore these for right now, we'll come back to these, but let's look at this area here. Okay? And in fact, if we look at that area, this was the slide I showed before, where that entrenched valley is completely flooded, really on almost a 10-year basis. Okay? If you look at that wide, dark blue, that's the floodway. Okay? No other place in our area has a floodway that wide. Okay? And I don't have a LiDAR image, but I've got a 1916 topo, and it shows the kind of fluvial morphology that is the record of the changes in the river with time. Okay? And so let's look at that a little closer. And clearly this river has had a whole series of meander cutoffs. So avulsion, at least of meander cutoffs, has been going on throughout time. Notice though there's no valley scale avulsion. The valley's too narrow. It can't take a new course. It essentially wanders throughout the entire course. Okay? Now, one of the areas I want to focus on is this area right here. Okay? And you see this levee. You see there's a cut bank like this. And notice there's some arcuate areas. Well, those are abandoned river channels. Now, the reason that's important is going back to that 1994 flood that was talked about earlier. In 1977, we see that much of the area has flooded, and that's because of subsidence. This is an area highly impacted by the subsidence due to groundwater withdrawal. You can also see we're beginning to have sand pits. And one of the problems with sand pits is that they have an unfortunate tendency of diverting drainage, particularly during flooding. Now, as it turns out, there are some pipelines that go through this area, and notice they cross the river. Now, where pipelines are required to cross rivers, they're required to be much deeper than the vertical scallop. But where they cross the floodplain, just bury them deep enough so that the backhoe doesn't hit it. Because after all, on the floodplain, there's either deposition or just flooding. So scour's not a problem, except when there's a meander cover. And so in that 94 flood, the river decided to take a shortcut. It broke through the levees. It went into the sand, and it ruptured the pipelines. And we had the greatest inland oil spill in U.S. history to that date. And when people asked, what do we do with it? I said, well, we just set it on fire. Because we hit a hot water heater. Okay? And that breach hasn't resulted in the complete rerouting of the river, but it's a major issue now and continues to be a channel rerouting mechanism. Okay, this attempted breach, and it was this breach and similar ones that resulted in pipeline signings the requirements to take into account avulsion. They had anticipated lateral migration. They had not anticipated avulsion. Now, the other thing about the San Jacinto River is there's a lot of sand mining. Okay? In fact, if you look at a map, a very significant portion between Lake Houston and Lake Conroe is sand mining. Now, ideally, you take the sand out and you leave some kind of a buffer. Okay? That would be what we would call floodplain or off-channel mining. And then that buffer prevents contamination of the water and also prevents a sediment from entering the river. Now, in fact, though, there's several types of sand mining, one of which is in-stream, where you literally go in the stream and take this stuff out. And then there's off-stream. In-stream mining has a huge amount of problems. Now, I'm not going to get into that. Off-site mining potentially is less of a problem if you have enough of a setback. And have enough of that protected boundary. In fact, you could argue that it's simply a detention pond. Well, it didn't always work that way. Because if you look at the development of the sand mining, well, this is off-site, but look at this one here. It not only isn't isolated from the river, it's purposely open to the river. And with time, it gets larger. We've got another one coming in here, and then the first flood, and another flood, and another flood. And so we can see that these sand pits are no longer hydraulically isolated. Now, to what extent that has changed the sediment budget, I can't say. But it's clear that it has the potential of rerouting the channel, changing channel morphology, and changing the sediment budget. So the San Jacinto River is relatively smaller than the Rose.
1 minute.
And I'm going to skip all this. Because I want to end with looking at Brays and Buffalo. We've seen this map, and I'm going to focus on these two bayous. Look how different the floodplains are. Okay? Brays bayou, the width of flooding is the same as the San Jacinto River. But the floodway is much smaller. Buffalo Bayou is much more narrow. Now, if you look at those and you ask the question, well, why is that? Well, the first is that Buffalo Bayou is an incised stream. It's cut down vertically. It's a much deeper natural stream. And by the way, because it's incised, it doesn't meander quite as much as it might otherwise. Gray's Bayou is actually a geologically younger stream, okay? And it is not incised at all. Now, we've got Buffalo Bayou has been protected by the dams. Dammed because of the 1935 flood. But one of the problems is that this drainage divide right here, it's a leaky drainage divide. Water from Cypress Creek spills over and floods. And so that increases the volume to the reservoirs. Plus the fact that reservoirs were dangerously in terms of maintenance, they were structurally unsound. And so the question is, why was that? Okay, well, I'll give you a very quick answer courtesy of Whitney Cyclin. And what he noticed was that if you look at these old maps, there's ridges, and these ridges have diverted the rivers. And these ridges were the old courses of the Brazos River. So if you look at the drainage today, and then if you look at those Pleistocene ridges, they're the drainage divides. And how did they get there? They got there because of high stands of sea level. Deposition, 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 deposition. These are all old parts of the Brazos River that during each of these successive high stands migrated downstream. So what that means is that the oldest streams are farthest inland, the youngest. The more incised streams are farther inland. And the ridges of the drainage basins, they get lower with time, hence they leak. And so it explains a lot of what we see in terms of pattern of flooding. Thank you. I have run out of time, but I'll be glad to answer questions during the break. Thanks.